Have a good day, Professor.
Thanks, you too.
No, it's like. See ya. When you go. Oh no, I just so. Yeah, sure. Yeah.
I was waiting.
It was fun. Yeah, tired.
Yeah.
Drank a lot of alcohol, but at least I remember what happened that night, which is better than a lot of people.
Yeah.
I didn't throw up either, which is better than a lot of people.
You stayed hydrated before too?
I did. I ate.
Liquid IVs?
I did. Yes.
Yeah,
Yes. We
those are
bought a
great.
bunch. Yeah.
Those are great. I love those.
No, it was fun. You know, it's crazy because, you know, it's the guy that was married. Like, he's one of my best buds from high school.
Yeah.
And so it's crazy because it's like you remember, you know, you see him up on stage. I mean, I was up there on stage with him, and you think about all, like, you know, the crazy dumb stuff you do as kids.
Yeah.
And now you grow up and then you're still doing really dumb stuff, but now it involves alcohol. And it's like,
Yeah.
man, my man he's made it, man. He's getting married, he's happy, and yeah, just it was all around just really great.
My best friend from high school, yeah. He's like, we were not the best kids.
Uh-huh.
Now he's a cop, he works full time.
Awesome.
He's got his he's like just bought his house, he has got a kid now.
Dang.
And I'm just like, I'm still in college. Like, I still have those memories, and like he's all bored.
It goes fast, man. And it's like, man, yeah, you look back and it's like,
Yeah,
you're kids
and
now.
it's funny because he was the worst out of all of us, and then he's like has the most serious jobs.
That's awesome.
Oh, me and
What's up?
Ozzy had a question for you.
Okay.
So it was okay. So you know how I asked you a couple of days ago about
simulating weight, right?
Yeah. Mhm.
So what I meant was, because we already have a geometry, because we're working on chassis, right?
Yeah. Mhm.
And there's gonna be, of course, there's gonna be weight on top of the chassis.
Sure.
So what I did was I simulated it as, I simulated a force putting down on it.
Okay.
So would that be the appropriate way to do it, or would it?
Is it-
can I
is
put
this-
weight?
Is this the weight of the chassis itself, or is this the weight of?
Or weight of something else?
Oh, okay, yeah.
Yeah,
That's
so
the best
force.
way.
So just
Okay,
on the base.
Just on the face of it. Okay,
And
yeah.
I know because Colin told me that, at least because when I ran the simulation, of course, I forgot at the time, but like this middle part was just like flat.
And we freaked out and we thought like, oh, let's redesign
But
it.
then when I read the numbers and it was like a small deflection, I was wondering, there was a way to see how it actually looks like, because I know
Yes.
this is an exaggeration.
Yes, and so there is a setting, and so by default, Ansys is going to exaggerate the deformation just so you can see it. But then there's a setting kind of near the top, and so it's a drop down menu, and so it'll say deformation scale or something like that. And then the default, it changes depending on the deformation. Like it'll probably be something like 10x, 20x, something like that. And so you can drop down and say true scale.
Oh, okay, that's gonna be really helpful.
And then you can see where.
Yeah, because I freaked out, and then until I saw the number, until I saw, or the actual number, it was like 7,000.
Yeah,
Yeah.
7,000. That's how low it was.
Yeah,
Yeah.
that makes sense. Yeah, 'cause the chassis is pretty strong. I mean, what was on? Like
It was
a
solid
Starbucks
wood.
stuff or something?
Oh,
no.
I was too lazy to actually do a tubular design, just because I needed to put
No,
sketch out.
and
Yeah.
because we're gonna put the arm on it, so the arm, we're trying to keep it like under 15 kilograms or like 35 pounds, so I simulated the 35 pounds.
Okay, yeah, 35 pounds not gonna do it.
Yeah, perfect. We went up to like what? We went up to like a ton.
Ton. Yeah,
We went up to like a ton, and there was some deformation, but it only went up to like this amount.
Okay.
So yeah,
That might be, wait, is the chassis just a solid block? of-
no.
I can actually sketch
It's
it too.
too, yeah, it's like.
Oh, okay.
So in the
For a
front,
ton, that's.
Yeah,
I
so-
expect a ton to do something.
the center of it will actually be composed of more solid rods.
Okay.
And then the actual like parts at the center, like the front and the back, will be tubular, just to
Okay.
save on weight.
Sure.
We have a new suspension system for our robot.
Yeah.
That mounts to the side, and we're concerned that depending on how it travels,
Uh-huh.
because it's also current right now, it's aluminum.
Yeah.
We're afraid it deforms too easily.
Hmm,
So we
I
just
see.
like,
Okay. Yeah, 35 pounds, I don't expect to do anything.
close.
But for a ton, yeah, maybe I'll take a look. Maybe I'll take a look later. But yeah, 35 pounds shouldn't do it.
Yeah. Okay. Yeah, it's great because I have this needs to be manufactured in like 2-3 weeks.
Yeah.
Okay.
And-
You need to get moving on that.
Yeah, and I already know the Symmetry is gonna have to deal with multiple things on like an assembly already put
Yes.
together.
Which is great because that's closer to what we need.
That's what I needed to do.
Okay, yeah. So it's it's activity 3.
All right.
Thank you.
Thank you.
Yeah.
Oh, thank you.
Oh. Okay, just leave it here and then. I'll
Let's
make
start
a
off
note.
with appointment.
Yeah, Wednesday, tomorrow, yeah.
Can I just go to your office?
I'm not gonna be here,
Not
so
gonna be, okay.
I work from home on Monday, Wednesday, so I'll have to be.
I was gonna just be here anyway, so it'll be easier.
Oh, yeah, I kind of fought for working from home. I live really far away from campus now, so any days I can work from home. It has to be. Under. Oh my gosh, 129. You were an old person.
It's a dog years.
I see.
There's only 18 years.
Not bad.
Wait, dog years is times 7, yeah?
Yes. Thursday.
Because I assume it's easy, but I'm like that many.
All right, it's 5:30. Let's go and get started. All right, good evening, everyone. How's everyone doing today? Good, good. That's right. I'm back. I'm back from the wedding. I survived, and so yeah, lots of it was a great wedding. Lots of good, a lot of funny things happened. You know, but just seeing one of my best buds get married is always such a thing. So I was telling someone before class today that I didn't throw up and I didn't black out, and so I think I didn't have as much fun as some other people at the wedding, but you know, it was still a lot of fun. So, but I'm back, and so you know, it's back to business now. Okay, so the plan for this week is that today we're going to be doing a lecture, so we're going to be finishing up. I have a little bit more I want to talk to you about boundary conditions, and then we're going to talk about material properties, and then Thursday we're going to do activity 3. Okay, and so activity 3 is kind of a good I would say break point, and so I consider kind of activities 1, 2, and 3 as kind of, you know, here's introduction to ANSYS. You know, we're still kind of getting used to the software. And so what you'll see next Tuesday, we're going to start talking about the midterm project. And so the midterm project, you know, I think after the first 3 activities, you're going to have enough practice with ANSYS to do the project. And so we're talking about the project on Tuesday, and that's going to be due by Halloween. I believe that's the due date. And so I give you guys about a month to do the midterm project. Okay. But activity 3, that's kind of, you know, after activity 3, that's kind of the end of, you know, introduction to ANSYS. And then for the rest of the activities for the rest of the semester, they're going to be a little bit more advanced, but also a little bit more specialized topics as well. So I think people generally enjoy, you know, the later activities more so than the first 3. Okay. Okay. All right. And so that's all my announcements. And so are there any questions I can answer before we get started for today? Okay. All right. So let's go ahead and get started. And so let's talk a bit more about boundary conditions, because there's a bit more I wanted to talk to you guys about. Okay. And so last Thursday, you know, we spent the day talking about, you know, the different types of boundary conditions that are out there, and you know, and kind of some little tips and tricks on how to apply them and what the differences are. Today, I wanted to start by talking about, you know, what I consider practical considerations when applying boundary conditions, which I think, you know, is kind of the more important part of, you know, of boundary conditions. Okay. So while, like I said, while it's good to know the difference between a constraint type boundary condition and a load type boundary condition, and, mathematically what they represent, at its core, this class is, it's a practical class, and how can you apply answers to problems, okay? And, I'd say probably the part that I think people generally mess up the most are actually applying the boundary conditions. And it was actually quite fitting, because actually, before the class today, I was talking with some people about how to actually apply boundary conditions. So this kind of fits pretty well with that. Okay. Because I will tell you right now that if you have bad boundary conditions that are not realistic, then your FEM simulations are going to be worthless. Okay. And that's even more so than the mesh, because even with the bad mesh, you might still be able to get some useful results. But if you apply your boundary conditions incorrectly, then your results are going to be mostly useless. Okay. Okay. And so I have mostly two kind of big tips for you in terms of how what you need to consider when you're assigning boundary conditions. Okay. Number one. And so the first tip is that the boundary conditions need to accurately represent how your system interacts with the external world, okay? Which is a mouthful, so I'll write it down. And so, kind of the spirit of this tip is that, when you're modeling something in FEA, when you're simulating something in FEA, right, you have your CAD model, which represents your system. And so that system is not just going to exist in a vacuum. Right? So that system is going to be placed somewhere in the real world, where the real world is going to be interacting with it. So it's going to be putting some kind of, forces, it's going to be putting some kind of loads, it's going to be constraining the object, in certain ways, okay? And so at its core, the boundary conditions represent how your system interacts with that outside world, okay? And so that's why, you really need to take some time to think about, how are external factors interacting with my system, and how can I encapsulate that within boundary conditions? Okay? Okay. And this is important because, your responsibility as kind of the finite element engineer is to choose the boundary conditions that best fit the physical environment, okay? And that might seem obvious, right? And so, of course, if an object is sitting on your structure, you're going to apply a force, okay? some cases are going to be really obvious, what the boundary condition should be. But there's also going to be a lot of cases where it's not going to be obvious what the correct boundary condition is. And it's kind of your job as the engineer to kind of, think about what's the best way that I can kind of mathematically or, physically kind of represent this. So this point is really important, and I really want to stress this home because you can run a simulation without without proper boundary conditions, because ANSYS is not going to give you an error. And so as long as you kind of as long as you satisfy kind of the minimum requirements where you have at least one constraint boundary condition and maybe a load or another constraint, ANSYS will be like, fine, you can run whatever you want, bro. Don't worry about it. But you're going to run into a situation where if you apply the boundary conditions incorrectly, your simulation is not going to reflect the physical result. Okay. And those are even more difficult to catch, because ANSYS is not going to tell you that this is not physical or this is not matched reality, because ANSYS doesn't know better. It's just a computer, right? And so, it's kind of really up to you, and you have to be the judge of, what's the best boundary conditions, and you have to be the judge of if the results make sense relative to the boundary conditions. Okay? I can't even begin to tell you, how many, even people that are in the field. So a lot of research presentations that just get absolutely just annihilated because people have criticisms of the boundary conditions. And so people ask, like, is that physical? Like, is that right? Is that the right boundary condition there? And so, wouldn't this one make more sense? And so I've seen just people just eviscerated over the boundary conditions. And so, you really want to take the time and think about what's the best, because there are situations where it's not obvious. Okay? And we'll do a bit of that on Thursday. So, I'll give you a bit of a preview. So Thursday, we're going to be doing another activity, and we're going to be doing an ANSYS simulation of basically a freeway signpost. And so, those signs you see over the freeway that show where the exits are. And one of the forces that we're going to apply is a wind force. And so, we're going to apply a force of wind that's been pushing on the sign. And we're going to be applying it as basically a point limit. So we're going to be applying the wind kind of at the center of the sign, just at a single point. And so, you have to ask yourself, is that really how wind acts? And so is the wind going to be acting just at that one point? Or is it better to kind of distribute that force across the entire sign? Okay. And so that's kind of one example of kind of the subtleties of, how you choose the boundary condition and how it can impact your results. Okay. So I want you guys to be thinking about that when we do activity on Thursday. Okay, and so the other consideration I want you to think about with boundary conditions is how you actually apply it to your model. And so boundary conditions can actually be applied on a number of different geometry types. So it can be applied on a surface, it can be applied on an edge or a point. Okay. And that applies to all types of boundary conditions. So that goes for all the constraint type boundary conditions as well as all the load type boundary conditions as well. Okay. Generally speaking, you want to, most of the time, you're going to want to apply the boundary conditions on as wide an area as possible. And so applying a boundary condition on a surface is preferable to an edge, and applying a boundary condition on an edge is preferable to a point. Okay. Surface, edge, it's greater than point. And the reason for that is it's a little bit hard to get into right now, but the reason for that is that you kind of get more stable and just better quality results if you can apply that over a larger area. Okay. That's not to say that there aren't situations where you want to apply a boundary condition on an edge or a point. It's just that generally, if you can avoid it, and if you can apply the boundary conditions over a 2D surface instead, that's generally going to be preferable in those situations. Okay. Great. All right. And yeah, and then that's it. Okay. All right. Any questions on this? All right. And so, I want you to kind of think about these two points, especially when it comes to boundary conditions. And so I think for activity 3, I think I tell you what boundary conditions to apply. And so it's a bit different than activity 2, where you kind of make it up on your own. But it's still good to think about, because I will be the first to tell you that activity 3, the way the boundary conditions are are modeled, I wouldn't exactly say that they're the best, considering what they're meant to represent. Especially things like weights or things like the wind force. I think there's better ways to do that. So definitely think about these as we do activity 3. Okay. All right. So the last, I would say, kind of the last piece of the puzzle, in terms of ANSYS basics that you should know, for every kind of ANSYS job that you do, are material properties. And we've talked about material properties a bit, and so this is not the first time, but I do want to kind of formalize it into a lecture so that we can kind of talk about some of the more finer points and some of the more nuance, okay? Especially some of the alternate material models that are out there. So even though we're going to be mostly working with linearly elastic isotropic materials, I want to make you aware of what some of the other tools are out there in terms of material properties. All right, so first let's define them. So material properties, what they refer to are the physical parameters of the material that affect how it responds to physical forcing. And so every object that has mass here on Earth, and I guess beyond in the galaxies and the universe too, we're all made of certain materials, right? And the materials that we're made of all have different properties. And so intuitively we understand this. And so plastic will behave a certain way, whereas a metal will behave a certain way. Okay, and depending on the properties of that material, it's going to respond differently. Okay? And so some examples of material properties that you've probably seen before are things like density, okay, or mass. Okay, things like the Young's modulus or strength. And if we're talking about dynamics, another important property would be like the coefficient of friction. And it's important to distinguish that, when I talk about material properties, I mean properties that are inherent or, inherent to the material itself. And so usually these are what's called intrinsic properties, which are, properties that don't change depending on how much mass or how much volume you have of something. Okay. And so one example of this, would be kind of the difference between mass and density. Okay. And so the density of a pound of aluminum is going to be the same as the density of 1,000 pounds of aluminum, right? Because density is a property that's intrinsic to aluminum itself. Okay. Whereas the mass of a pound of aluminum is going to be very different than the mass of 1,000 pounds. Okay. And so these are properties that are just intrinsic to the materials and doesn't really have to do with the shape or geometry or amount or whatever. Okay. So mathematically, the reason we need to input boundary conditions for finite elements is that the material properties are used in the governing differential equations. Yeah. And so things like the density, things like the Young's modulus and the Poisson's ratio. So all those parameters, they enter into the governing equations. And thus, as ANSYS goes and solves the governing equations, the material properties are going to affect the solution. Okay. And so, because they make such a big impact on the solution, it's just like the boundary conditions. It's important to make sure you choose the right material properties for your system. So we haven't done too much with material properties yet in our first two activities. I think for our first activity, we just used the default one that's in ANSYS, structural steel. And I think in the last activity, we just input it because of a very simple met, aluminum 6061. Okay. But material properties, is actually goes a lot deeper than that. And so, when I say choose the right material properties, it's a lot more than just choosing the right Young's modulus and the right Poisson's ratio. Because that's kind of the simplest material that you can have. And so in addition to choosing the right property values, you also have to choose the correct or the most physically realistic material model. Okay. And so we'll talk a bit more about what material model means, but basically there's different mathematical representations for how to basically model or how to basically capture a material's behavior. Okay. And so, I think we've talked about linear elasticity, quite a bit in this class, and so that's one such material model, but there's other ones out there. So, just for this class, we're going to talk about things like anisotropy. And so if you have an anisotropic material, we're talking about plasticity, and we'll talk about probably something that you may or may not have heard of called hyperelasticity as well. And so that's another type of material model out there as well. And question.
How close, like entering the temperature and stuff like that when we're doing this test?
Yeah, no, great question. So, temperature is another kind of ambient condition that can affect the material properties. And so, if a lot of the material properties, they change with temperature, especially things like density. And so it is extremely important. And so, if you really want to have an accurate simulation and your system's going to be exposed to adverse temperatures, either very high or very low, it's important to make sure that you capture those temperatures as well. And so it's actually very common to run kind of a thermal simulation right alongside a structural simulation. So you can have those dynamic changes in temperature, and those will actually change the material properties kind of in real time as well. And so that's something that's used quite a bit. All right, and so out of everything that we talk about in terms of the basics, in terms of meshing and boundary conditions, I would say material properties is the part that I personally know the least about, just because my background is more in fluids and thermal, and so I know there's a whole world out there of structural material models and material parameters and a lot of different models for that. And so I will say that beyond what we're going to talk about today and maybe a little bit Tuesday, that's kind of the limit of my knowledge, but I know that there's a lot more out there. And so if you want to learn more about this, I would talk to some of our structural faculty here, so maybe like Dr. Lee, Dr. James, Dr. Sue. I know Dr. Sanders. I know they know a lot more about this stuff than I do. So, but I can at least give you the basics in terms of what you need to know to practically apply this in ANSYS. All right. Any questions on this? All right, so let's start going over the different material models and kind of what you need to specify for each of them. Okay? And so let's start with our favorite one, the one we're going to be using for most of this class, linear elasticity. All right, linear elasticity. And so, I think, this may be the third time that we've talked about this in this class, but linear elasticity refers to materials where the relationship between stress and strain is purely linear. It's the simplest one out there. And so, that's kind of why we use it. And so in terms of the number of parameters that you have to specify, linear elasticity has the smallest requirements. Okay. All right, and so graphically, let's go ahead and draw the graph. And so you've probably seen this a million times now, but a linear material model, something like this, okay? And so we have stress on the y-axis, strain on the x-axis, and the relationship is just a line like that, okay? Where again, the slope of this line is the Young's modulus. Young's modulus E, okay? And so like I mentioned, it's a popular one to use, especially when you're kind of first learning ANSYS, you're first learning about structures, because it's the simplest. And so, you really only have to specify 2 different material parameters, which we did in activity 2. Okay. And so let's go over what those parameters are and what they represent. Okay. So let's do the Young's modulus first. So the Young's modulus is E. Okay. And so just like I mentioned above, the Young's modulus is the slope of the stress strain curve. Okay. And what it represents is represents how well the material can resist deformation. We kind of use the Young's modulus as a measure of the material strength. Okay? And so a material with a higher Young's modulus, we associate that with being a stronger material. Okay. And so, intuitively, if you look at the graph there, and so if you have a material with a much higher slope, okay. So, let's say that we have a material has a relationship like that. Okay. And so the slope of this line is much greater than the black line. Okay. And so what that means is that in order to cause, a similar amount of strain, right, a certain amount of strain, you're going to need a much higher amount of stress, and much higher stress means more loads or higher amount of load. Okay. And so if you have a higher Young's modulus, that means you have a much stronger material. Okay. As an example, using 2 metals that you're probably familiar with, and so steel we generally regard as a very strong material. Okay? Steel has a Young's modulus of about 200 gigapascals. Whereas copper, we all consider copper to be a much softer material. Copper has a much smaller Young's modulus of about 130 gigapascals. Okay. Okay. And so generally, when you're thinking about the strength of the material, how strong it is, how well can it resist deformation, we rate that based on the Young's modulus. All right, any questions on that? All right, so next we have the Poisson's ratio. And so Poisson's ratio has the symbol nu. Right, it's a Greek letter. It looks like a fancy V. Okay. And so what the Poisson's ratio measures is that it measures how much the material will deform in directions perpendicular to the load. Because oftentimes, when you have a 3D part or a 3D geometry and you apply some loading in one direction, because of conservation of mass, you're going to have deformation in directions that are perpendicular to it. Okay, and I'll draw a picture to kind of explain that in a second. But let's define the units for Poisson's ratio. First of all, there are no units, and so the Poisson's ratio is just it's a ratio, and so it's something that either can be 0 or 0.5. Right, and so if you have a Poisson's ratio of 0, this basically means that you have almost no perpendicular deformation. Whereas a value of 0.5 is lots of perpendicular deformation. Okay. So let's do a quick illustration of this. Okay, and so let's say that we have a bar. I guess it's a rectangle. Let's pull on the bar in tension. Okay. So we're taking our bar and we're just kind of pulling it apart just like that. Okay. Very similar to our first activity. And so what we generally expect is that after we apply this this force, because the force is tensile, then we expect our rectangle here to elongate. Okay. Okay, so we have an elongation due to loading. Okay. And so the elongation is a deformation that's in the same direction, or it's parallel to the loading, okay? Because the loading is going left to right here. And so elongation means that's deformation in that same direction. Okay. But in order to satisfy conservation of mass, what needs to happen is that there needs to be some of this that's occurring. Okay. Right, and so you can't just stretch a piece of material and expect it to stay the same width, because otherwise that's going to violate conservation of mass. And so to kind of compensate for the fact that the overall length is getting longer, then parts of the geometry are going to get skinnier, to compensate for that loss of mass. And the degree to which you see the material gets skinnier and how localized it is or not, that depends on the Poisson's ratio. Okay, so that's Poisson's ratio there. All right, any questions on Poisson's ratio? Yeah.
Would a material with a Poisson's ratio of 0 still be able to elongate?
That's a great question, and that would be probably a better question for one of the other structural faculty. Yeah, this is the Wikipedia definition of Poisson's ratio. Yeah, I've wondered that for a long time too, because I know that most of the materials that we work with have Poisson's ratio somewhere in the order of 0.3, 0.5, and that has to do with the fact that the material is incompressible, and so it roughly kind of maintains volume when you stretch it. And so to kind of compensate for the fact that it's elongating, the thing gets narrower, so you maintain the same mass, the same volume. But I don't know of any solid materials that have a Poisson's ratio of 0. And so I'd have to look into them more and kind of get back to you on that. But I know that most of the ones that we work with are like 0.3 and above. Okay. All right. And so those are the two main properties that you have to specify. And so if you think back to our activity 2, when we were specifying the material properties for aluminum, these are the two that we specified. Okay. There's actually a third material property for linear elasticity that no one really talked about. It's like a forgotten cousin, and that is called the shear modulus. So the shear modulus determines how strong the material is or how much the material resists shearing deformation. Okay. Okay. So, once again, because, we're working with three-dimensional objects most of the time, there are certain situations where our materials will be loaded in shear, okay? And so the shear modulus here tells you how well the material can resist shearing forces, okay? And so the reason we don't really talk about the shear modulus too much is that if you have an isotropic linear elastic material, you can compute the shear modulus based on the other two properties, okay? Okay. And so the symbol for shear modulus is a G. Okay. And so G is computed as E, which is the Young's modulus, divided by 2 times 1 plus nu, the Poisson's ratio. Okay. And so some of you might have noticed this when we did activity 2. So activity 2, when we were specifying the material properties for the aluminum, we only did the Young's modulus and the Poisson's ratio. There was actually another entry there for the shear modulus. If you kind of just look a couple rows down, but what you'll probably have seen is as soon as you entered the properties for the Young's modulus and the Poisson's ratio, the shear modulus gets automatically calculated based on that formula there. Okay, and so because this formula exists, we only have to specify E and nu. Okay. All right, so those are the main parameters that are needed for linear elasticity. And so, we spent a bit of time talking about them because it's good to understand these. Because, like I said, for most of the activities in this class, of course, for the project, you're free to do otherwise. But for at least for the activities, we're mostly going to be working with linearly elastic materials. And so it's good to kind of understand, what the material parameters actually physically mean. Okay. Next, let's start talking about the differences between, isotropic, orthotropic, and anisotropic. Okay. And so I mentioned isotropic, just in the line above this, okay, when I talked about that formula. But what does it mean? Okay, so isotropic basically means that the strength. An isotropic material means that the strength of the material is the same in all directions. And so in other words, it doesn't matter which way that you load it, you're going to observe the same strength of the material. Okay. Let me draw some examples here. Okay, so let me draw a cube. Cube 1, cube 2. Okay. Use your imagination and pretend all 3 cubes are identical. Okay, I know I didn't draw them up, but that's besides the point. Okay, and so for an isotropic material, that means if we load this cube this way, okay, or if we load this cube this way, or if we load it this way, right? And so we're loading the cube in 3 different directions. But if we assume that the load magnitudes are the same, and so we have P and load of P, for each of those directions, then we're going to experience the same amount of strain, the same deformation. Okay.
All perfect cubes.
Yes, they should all be perfect cubes.
Something that can only happen.
Well, I picked a perfect cube because you can kind of just rotate it either way. And so if you load it in this direction versus this direction, you just have to rotate the cube. And you get literally the exact same deformation field. But the isotropicness doesn't depend on the shape of the material either. It's just it just measures the strength of that material in each direction. Yeah. Okay. This is the reason why, for the most simple linearly elastic material, we only specify we basically just specify one strength parameter. And so that's just the Young's modulus. Okay. And so for an isotropic material, you only need one parameter to describe the strength, and that's the Young's modulus. And so what that's basically saying is that the Young's modulus will describe the strength in every single direction. So, I'm showing you 3 directions here, and so it's basically X, Y, and Z direction. But that applies to all the obtuse directions too. So if you kind of squish the cube diagonally, or you squish the cube diagonally the other way, and so you're still going to observe the same strength because it's just one Young's modulus that's working for all of them. Okay. So when we can work with an isotropic material, it's the simplest that we can do, and we generally like doing it because it's the simplest. Okay? And so when is it appropriate to use an isotropic material? Okay. And so most metals are considered isotropic materials, and that's a direct result of its molecular structure. And so if you kind of know a bit about how metals are molecularly organized, all the molecules are organized, very, very orderly. So they're all kind of right next to each other in perfect little lines and perfect little order. And so, because of that, you get kind of the same material properties no matter what direction you go in. Okay. And that's great for us because metals are a very common engineering material because they're relatively cheap, and they have a lot of strength for their cost, and they're relatively easy to machine too compared to some other materials as well. Okay. Any questions on isotopic materials here? Okay. All right. And so, what are the other types of directions that are out there? And so, there are ways that we can model situations where the strength is unequal in each direction. And so I think one material that we talked about earlier in this class is wood. Okay, and so wood is a very famous kind of non-isotropic material because wood has these grains that are running through them. So depending on which direction the grains are running, that's going to alter the strength of the wood. And so the question is, how do we actually model this within ANSYS? And so how do we input, different strengths in different directions? Well, there's a lot of options for it. So there's kind of way more options that we can cover in just one lecture. But I do want to mention the two more common ones that you can use. Okay. All right, so the first type of non-isotropic material is orthotropic elasticity. And what you'll see, in contrast with the isotropic material, which only had two material parameters that we had to specify. So we only had to specify the Young's modulus Poisson's ratio. What you see is that if you add complexity in terms of, strength in different directions, it's going to require more parameters that you have to specify. Okay. And so actually, one of the more simpler ones is orthotropic, but even the simpler one requires 9 material parameters to specify. Okay. Right? But this one's popular because, even though 9 sounds like a lot, the 9 parameters are actually, very intuitive if you have a good grasp of isotropic elasticity. Okay. And so here are the 9 parameters. And so first you have to specify Young's modulus, or Young's moduli, in all 3 directions. Have to specify Poisson's ratios in all 3 directions. Okay. So that's X, Y, and Z. And then you have to specify shear moduli for all 3 directions as well. Okay. Right. So 9 sounds like a lot, but I think by this point, we understand what the Young's modulus represents. We understand what the Poisson's ratio represents. We know what the shear moduli represent. And so now you just have to specify them for each direction kind of individually. Okay. And orthotropic elasticity is a very popular choice for modeling woods. Okay. Because for woods, like I mentioned, the grain direction is something that's important. So a lot of times you can kind of modify your CAD model so the grains run in either the X direction, the Y direction, Z direction, and then you can alter the strengths of the Young's moduli, the Poisson's ratio, and the shear moduli based on the directions of the planes. Okay. And so you'll see quite often actually that, if you have wood, if you're running a finite element simulation of a wood model, then you're going to use an orthotropic material to model. Okay. And so the other material model that I want to go over is the anisotropic material. And so the anisotropic material model is probably the most, the most inconvenient material model to use, but it also gives you the most flexibility. Okay, and so orthotropic elasticity, we made a big jump from 2 parameters to 9. For anisotropic elasticity, we're going to make another big jump, and so we're going to go from 9 parameters to 27 material parameters. Okay? So anisotropic materials are kind of for the materials nerds, who like to modify every little detail. Okay. So the reason there's so many of them, and the reason there's a lot less in the other material models, is that anisotropic elasticity makes no assumptions on symmetry. Okay. And it's hard to, it's a little bit hard to kind of get into a discussion of what symmetry means in terms of material parameters without, probably without bringing Dr. Sanders in here to kind of explain it for me. But, for the other material parameter or material models like orthotropic elasticity and isotropic elasticity, there's a lot of symmetries that are involved. And so you kind of assume that if one thing is happening in one part of, in one direction of the geometry, it's going to be happening also in another part. Okay, or another direction, I should say. And that goes for the XYZ directions, but also goes for all of the shear directions as well. And so, XX, XY, XZ, YX, YZ, all those directions. So there's a lot of symmetry that's kind of implied by orthotropic elasticity and isotropic, but an anisotropic material makes no such symmetry assumptions. Okay, so that's why it requires 27 parameters. Okay? Right. And so, generally it is very rare that you need to specify a fully anisotropic material unless you're working with a very, very strange, maybe a composite material of some kind that you're kind of cooking up, from scratch. But if you're talking about just kind of naturally occurring materials, it's very rare that you need a full anisotropic elasticity to kind of capture it. Okay. The only thing I can think of in practice that you might have to do this for is some kind of biological tissue. So biological tissue behaves quite strangely compared to some other materials, and so sometimes you have to use an anisotropic material to really capture its behavior. Okay, but for most kind of normal materials, it is pretty rare. But I do want to make you aware that it's out there, kind of what's required. Okay. And so before we kind of move on to plasticity, I did want to mention that, for most, when I talk about all these parameters, the 9 parameters, the 27 parameters, and even, for isotropic elasticity, just the Young's modulus and the Poisson's ratio, these aren't just made up, right? And so, God didn't just say like aluminum has to have this material property, right? And these aren't being made up by engineers as well. And so the way that we typically find out these material parameter values is through some kind of mechanical testing. Okay. And so you might have done tests like this in some of your lab courses. So you've probably done like a tension test, and so you probably stuck a piece of metal inside a machine and it kind of pulls it apart, and you measure the relationship between force and the amount of strain that you measure. Okay. And if there are a lot of tests, like there's that test, of course, but then there's a lot of other tests like biaxial testing, things like that, that scientists use to determine what these parameters are. Okay. And so when you see that the Young's modulus of the material is this, just know that there's probably a wealth of laboratory tests that kind of support that. Okay. And so, at this point anyway, there's no way for us to kind of, just for instance, maybe look at the molecular structure of a material and determine the Young's modulus from that. So most time it's done experimentally. So, we've put the material under strain, and we've recorded the properties. Okay. And so if you have a relatively new material, it might be hard to find reliable data on its properties, just because perhaps there's just not been enough testing on that material, to really get a good sense of what the properties should be. So it's something good to keep in mind. All right. Any questions on this? All right. And so let's go ahead and move on to another type of material model out there, which is plasticity. Okay. And so, everything that we've covered so far kind of still belongs in the realm of linear elasticity. And so even for an orthotropic material and even for an anisotropic material, you still have this linear relationship between stress and strain. It's just that for an anisotropic material, the stress in one direction is related to the strain in another direction, by different parameters. Okay? And so it's a bit not so straightforward, but the relationship is still linear. And so once you start talking about plasticity, that's when you start to break kind of that linear relationship. Okay. And the way I phrase that is kind of important. So, when I say this is the point, and so what I mean by that is, for a lot of materials, if the stresses and the strains, or I should say the strains, if the strains are kind of kept relatively small, most of the time you observe just linear behavior. Okay, but if you keep deforming the material and the strains kind of exceed a certain threshold, that's when you start to see plastic behavior. Right. So what do I mean by plastic deformation? Okay. So if you're in the linear range, okay, and so if you had the small deformation, small strains, kind of the assumption is that if you release the load, then the material kind of returns to its original shape, okay? So let me kind of draw that kind of visually for you. Okay. So here we have our stress strain curve. All right, and so let's say that we have a material, you know, where they have a linear stress strain curve like that, okay? And so let's go ahead and define this point here. And so the origin here, this origin is when the material is at rest. Okay? Okay. And so when the material is under no loads, then there's no stress, then there's also no strains as well. So the material kind of retains its original shape, okay? As the material is loaded, so let's say that, you know, we start to apply loads on the material, you know, we start to climb up this graph, okay? And so let's say that we apply, you know, maybe a moderate amount of loading onto our material, then the stress, you know, it causes a stress level of this right here. And that stress is enough for the material to strain by an amount right here, okay? And so as we apply some external forces, you know, maybe they're tensile forces, maybe they're compressive forces, you know, the stress in the material is going to increase to keep it, you know, keep the material in equilibrium with the outside forces. And the material is also going to strain according to this relationship right here, okay? But, you know, if we only strain it up to this point, if we only stress it up to this point, and we release the load, okay? Okay. If we're still in the linear region, then what's going to happen is that the material is going to return to its rest state, okay? And so the linear part of the stress strain curve here is like kind of like a, you know, a two-way road. And so you can go up the ramp, you know, when you're loading the material, but when you release the load, you go back down the ramp, okay? And if all the load is released, then you return back to the rest state, which is great. Okay. But notice, you know, notice the way that I drew this was that, you know, the linear portion only goes up to a certain point, okay? Because for many materials, once you kind of get past this, this point right here, the shape of the curve changes, okay? And so this point right here, where the shape changes, we call this the elastic limit. And this region of the curve right here, where the stress strain relationship is no longer linear, we call this the plastic region. Okay. And so let's see what happens, you know, when we start to load a material past its elastic limit. So let's go ahead and load the material. Okay, so I'm going to use purple this time. Okay. Okay. And so the first thing you'll notice, and so let me go up to here. Okay. And so if you load the material past its elastic limit, you know, what you'll start to see is that the stress strain relationship is going to be changing. Okay. And so you no longer have a linear relationship. But what you have instead is that, you know, the more stress that you put in, because the curve is kind of flattening, you know, you're going to get more strain. So it suddenly becomes, you know, a bit easier to cause more deformation because the strength is kind of reducing. Okay. The other consequence that you have is that if you release the load, kind of once you've kind of exceeded past this elastic limit, and so let's say right here, we release the load. We're no longer able to return to the resting state. Okay? And so from here, what's going to happen is that the material is going to relax, but it's not going to relax back to its resting state. Okay. And so whatever point that the material left off on, it's going to start to relax from there. The slope of this line, this relaxation line, this is still the Young's modulus. Okay? And so it has the same slope as the linear region there on the left, but you can see that it's offset because we've entered the plastic regime. Okay? And so this point right here, when the load is completely released, this right here is the new resting point. Okay. But of course, it's not the original resting point. And so there's kind of been some permanent deformation that's occurred that can't be undone because you've exceeded that elastic limit. Okay. So hopefully that's a review. So hopefully you've seen that before in solid mechanics, but this is just kind of a refresher of what is meant by plastic behavior. Okay, so plasticity kind of means two things. And so on the first hand, the relationship between stress and strain changes, and so it's no longer linear. But also you have this effect of kind of this permanent plastic deformation that's always going to be there. All right, any questions on this? Our question is this kind of how strain hardening works? Yes, yeah. And so strain hardening works in that, in that same way. And actually, understanding strain hardening is a good way to understand how it's actually implemented in ANSYS as well. So I don't think we'll have time to cover both, but we'll pick this up next Tuesday. When we finish up these lectures. All right. Any questions? Any other questions on this? All right, and so there are only 3 minutes left, and so the next thing I was going to talk about is how this is actually applied in ANSYS, but I don't want to rush through that. So let's go ahead and save that for next Tuesday. Okay, and so for now I'll just say that there are multiple ways to implement in ANSYS. Okay. And then we'll pick it up on Tuesday. And so we'll talk about those two ways that you can implement plasticity in ANSYS. Then we'll talk about hyperelasticity, and then we'll go ahead and move on to the next topic. Okay. But on Thursday is going to be an ANSYS activity. And so, I know people like to be here during the ANSYS activities because that's, it's an easier way to get help. And so on Thursday, we're doing another ANSYS activity. That's the last one of what I call the ANSYS basics. And then next week, we'll talk about the project. Okay. So thank you everyone for coming today. Take care of yourselves, and I will see you guys on Thursday. Thanks, guys. Okay. Yes.
So I would we have to make the appointment on the EGME or I can be available on the office hours there.
So the office hours, I reserve those if they answer questions about the class. I prefer you make an appointment, because if you make an appointment, you have kind of a whole conversation there to kind of log the fact that you made an appointment and you came for that, and then it'll automatically kind of release your papers. So yeah, I do prefer that you make it, because otherwise I have to go make that.
And for the appointment, it's on a week.
Yes.
And before I normally saw
Professor Stacy. Yeah.
So he's no longer here, or
He's not
changed
here.
the department?
So I haven't heard a straight story what happened with Professor Stacy. I know that he's not here this semester, but I don't know if he's coming back. And so me and Dr. Lee are here for now. And the other advisor last year was Dr. Weiss, and she is on sabbatical, so she's unavailable this semester, but she's coming back next semester.
And when with the appointment, it will be on Zoom or in person?
For all of mine, they're on Zoom, because I do my appointments on Monday, Wednesday, Friday. And those are days that I work from home. I think Dr. Lee, you can meet in person.
I mean, you know me, so I prefer to move it up.
Okay, yeah. I mean, for some it's very fast. And so what we're required to do for the advising is, go over your TDA and just make sure, and then we kind of construct a study plan for you. But for some students, a lot of them kind of already know what they have to take, especially at this point, if they're close to graduating. Then the meeting is very quick, and so I try not to keep people longer. So.
And another thing, for the elective classes, we can only take 2 at a semester, or we can take 1.
Oh, you can take more than 2. I mean, there's 4. You need to take 4 in total.
4,
Yeah, so you can take more than 2. Of course you can.
For example, this semester I take 2.
Yeah.
Next semester I will take 2.
Uh-huh.
But if for some reason I can't go on with the other class, and so I will if I drop it, so the next semester I can take.
Yes.
3.
Yeah, no problem. You need to have 4 before you graduate. That's
Thank you very much.
yeah, no problem. Okay. Thanks for letting me know, Charles. Yeah, I didn't know that. Charles, Joshua, any final questions before I close it up? Okay, all right. I'll see you guys on Thursday.